Oh, didn't get the little message. Uh, so Dusty Madison is our newest professor at UOP. This is his second semester. We haven't scared him off yet. And he's from Ceres. So he ended up not far from where he started. He got his first schooling at University of California at Berkeley and went from there to Cornell, which is also where Neil Lark went to school. And so from Cornell and ended up back here in Stockton. So we are really fortunate to have him back this way. His primary field of research is gravity waves, and gravity waves have only been detected fairly recently. So that is, the cutting edge of research in astronomy these days. He's part of the nanograv collaboration, which I'm hoping to hear more about. Um, and like I said, it's continuing work in gravitational waves and is familiar with the LIGO program. And he is here to enlighten us on gravity waves. Hope that none hit us very soon. No. Anyway, please welcome Dr. Dusty Madison.
Yeah, thank you for having me. Yeah, so I'm going to be talking about this exciting new area of research. It's really a new frontier. We're doing astronomy unlike anything that's ever been done before. The last sort of 6 years has been full of breakthroughs. So yeah, I'm a new professor at UOP. I'm a member of this collaboration called Nanograv that I'm going to be talking about more in a few minutes. And thanks for having me. So let's get into it. I mean, what is astronomy, or what has it been for the last few centuries or since antiquity? It's more or less this. You go out, you use some kind of instrument like a telescope. You look up at the sky and you look at, the sky is filled with a bunch of stuff. There's stars. In this image, you can see the Milky Way, which is filled with gas. You can see gaseous structures in space. But everything that you look at in astronomy is light. You're just seeing electromagnetic waves from space. And so in a little bit more like excruciating detail, like what's going on here? You have something like a distant star that is, very far away, several light years, several hundred light years, maybe a million light years, something like that. But this star produces light in some way, and that light just travels as an electromagnetic wave through the vacuum of space, just unimpeded. And some, long time later, it reaches some sort of receiver on our end. And for optical light or visible light, it might as well be our eyes. These were the first astronomers, right? People who just looked up at light that had traveled across the vast reaches of space, and it hits our eyes, and you learn something about what's out there in outer space. Now, in the last, few decades, we've gotten a lot better, or we've managed to build much better instruments than just our eyes for studying optical light or visible light. Oh, pardon me. I wanted to say this. I'm going to be talking a lot about like frequencies and wavelengths and stuff, not just of light, but also of gravitational waves. So just keep in mind this relationship, that the wavelength of light or the wavelength of gravitational waves, which I'll be talking about, it's just related to the frequency by you take the speed of light and divide by the frequency. Anyways, we've done a lot better than our eyes over the last century or so. We build things like the Keck Observatory. We build these gigantic light buckets on the tops of mountains, and they just allow us to see things that are extremely faint, very, very far away, billions of light years away. This is sort of the state of the art for optical visible light astronomy, right? These world-class observatories. But again, this is just like the visible light spectrum. There's a whole lot of electromagnetic waves out there that aren't visible light. In fact, visible light is just this super tiny little sliver of the full electromagnetic spectrum, right? And so if you want to do something like ultraviolet astronomy, I mean, there's a lot of stuff in space that produces interesting ultraviolet signals. How do you study it? Well, it's both good and bad that our atmosphere is pretty good at blocking out most ultraviolet light. So if you want to study the ultraviolet light that's being produced from things in space, you really need to go to space. This is one of the great strengths of the Hubble Space Telescope. So Hubble is maybe best known for its capabilities with visible light, but it also has ultraviolet detectors on board that you can't do the type of ultraviolet astronomy that Hubble did from the ground. Okay, so you need to go to space for stuff like that. What about other sort of windows of the electromagnetic spectrum? So I have a lot of familiarity with radio astronomy. My collaboration does a lot of radio astronomy. Radio is nice because, well, I mean, radio travels very easily through our atmosphere. Our atmosphere is basically transparent to radio waves. That's why we have radios. You can tune into your local, classic rock station or whatever, and it's being transmitted from dozens of miles away, and the light just travels easily through the atmosphere, no problem. And so we can build these gigantic telescopes on the ground and just look straight through our atmosphere at the radio signals that are being produced in space. So, I mean, this is the Very Large Array in New Mexico on the left, and the Green Bank Telescope on the right. So the Green Bank Telescope is in West Virginia. Jerry said, I did my graduate school at Cornell, but after graduate school, I lived in both Virginia and West Virginia. West Virginia is like a great sort of center for radio astronomy, specifically because of the Green Bank Telescope, which is in sort of rural West Virginia. Anyways, my collaboration uses both of these telescopes extensively, especially the Green Bank Telescope. So, I mean, what's the point of all of this? Why go to the lengths of building things like the Hubble Space Telescope or the new hotness, the JWST? It's because whenever you study sort of different areas of the electromagnetic spectrum, you learn altogether new things about the universe we live in, right? So this is just an image of the Milky Way in 5 different sort of wavelengths. And you can see they're all vastly different. They tell us about different processes that are going on. They tell us about different sort of epochs of star formation and sort of magnetized gas. If you want to get a full picture of like what's going on in space, you need this sort of multi-wavelength approach to astronomy, okay? So this is my sort of like primer on classical astronomy. And now I'm going to jump into talking more about gravitational waves, okay? So what are gravitational waves? Well, in the early 1900s, I mean, this is all Einstein. He developed our sort of modern understanding of gravity as a curvature of space and time generated by massive objects. So no longer is it that the sun sort of is pulling on the Earth through some sort of like Newtonian gravitational force. It is that we live in what wants to be a sort of flat geometric space-time, and the presence of mass like the sun warps that space-time. And the Earth is just trying to move in like a straight line through what is now a warped space-time, and it can't, so it moves in sort of an elliptical trajectory around the center of this warping. So this is like the modern picture of gravity. It's weird to say that it's modern because it's over 100 years old, but this is, again and again, Einstein's theory of gravity is just like holding up. And one of the like latest sort of most impressive tests that it has held up to is this thing that has to do with gravitational waves. So in Einstein's theory, one of the consequences of his theory is that if you have massive objects like stars, specifically compact stars, like say like white dwarf stars or neutron stars, if you have 2 of them orbiting each other, they produce these sort of dynamic time-dependent curvatures of this space-time that radiate outward as waves. And these are what gravitational waves are. They are ripples in space-time. If you have dynamic systems like compact orbiting systems, they sort of just whip up the space-time and you send out waves like this. So, these are very different than electromagnetic waves. Like how can we even like think about these? These are waves in space-time. This is sort of one attempt at visualizing what they might look like. If you can kind of imagine space-time as like almost like a Jello mold, this is what would happen to space-time as a gravitational wave sort of propagates sort of out of the screen. It sort of, in an undulating fashion, it kind of squishes space along one dimension while stretching it along the other. And then it like squishes it along the first dimension and stretches it along the other. So you get these sort of undulating strains, we call them, of space. And they move, or the strains are sort of transverse to the direction of propagation. So it's very similar to electromagnetic waves in some ways, in that it's a transverse wave that is traveling like at the speed of light. But it's a wave sort of in the fabric of space-time itself. It is a stretching and straining and squishing of the space between free-falling objects. Okay. So I mean, yeah, the gravitational waves are very different than light, but I mean, they have a lot of nice features of that are very similar to light. They travel through space sort of unimpeded. They don't sort of damp out as they travel through space. So they can travel across the cosmos. They can travel, billions of light years unimpeded. And, they're created by astronomical objects. These sound like perfect candidates for a sort of like altogether new type of astronomy. And that has been the long-term goal of gravitational wave astronomers. But how in the heck do you detect these things? You can't use your naked eye. You can't use any sort of conventional electromagnetic telescope. How do you detect these things? Well, I mean, spoiler alert, we have successfully detected them. I'll talk about that in a second. But so the idea behind how you detect them is you take advantage of this sort of undulating pattern that a gravitational wave produces. So the way to think of this sort of squishing and stretching ring of particles is, imagine that these were like little marbles floating in space. As a gravitational wave sort of propagates through this ring, you actually sort of stretch and squeeze the space between the marbles, and their physical distance, the physical distance between these sort of free-falling objects actually changes, okay? And so the LIGO collaboration, LIGO stands for Laser Interferometer Gravitational Wave Observatory. It set out to just do a very sort of brute force measurement of these types of changes in the physical distance between free-falling masses. Okay, so I mean, this is a sort of bird's eye view of one of the LIGO detectors. There are, there are two LIGO detectors. There's one in Washington State and one in Louisiana. I believe this is the one in Washington. But so one of the reasons this is a bird's eye view is the influence of gravitational waves on a detector like LIGO. Basically, the effect of the wave gets bigger as your detector gets bigger. So you really want to build a really big detector if you want to detect a small effect from gravitational waves. And so the LIGO detectors, they're these L-shaped interferometers that the arms of the interferometers are 4 kilometers long. So you have 4 kilometer long arms. At the like vertex of the two arms, there's a very sophisticated sort of optical system of very sophisticated laser technology. Okay, but basically what they're trying to do is just measure the arm length of these 4 kilometer long arms to extremely high precision, and to look for a specific pattern of sort of changes in the length of their arms that they could ascribe to a gravitational wave. Now, I mean, one of the reasons you have to make the detector so big is because the likely sort of gravitational wave sources that LIGO was looking for are very far away, billions of light years away. And also, like, space is just stiff. It's not super amenable to these waves. And so the anticipated deformation of the LIGO detector from gravitational waves was about 1% the size of a typical atomic nucleus. LIGO is a stupendous engineering feat. It has done feats of metrology that have never been done before. So, I mean, they were monitoring the lengths of these 4 kilometer long arms to a precision of like the fraction of an atomic nucleus. It still baffles me that they managed to pull this off, but they did. They did. Despite the tremendous technical challenges, in September of 2015, they succeeded. They detected, this is data from their initial detection. They detected gravitational waves from, it was the merger of two black holes. They estimate that the source of the the source of the gravitational waves was about 1.3 billion light years away. And the two black holes had a combined mass of about 65 solar masses. And so, yeah, this was the sort of dawn of an altogether new type of astronomy. I mean, this is, it's really a new era. And so for the first time ever, scientists used gravitational waves rather than light as what we call a messenger to learn about this exotic object in space that doesn't even produce light. I mean, these things are black holes. This was the merger of two black holes. Sort of the hallmark of black holes is they are black. They don't emit any light. So this is not the type of thing that you could even study with any type of conventional astronomy. You need this altogether new type of gravitational wave astronomy, okay? And yeah, so, I mean, it succeeded, but we've done a first detection. In a metaphorical sense, we're at the outset of a new type of astronomy. We are at the Galileo makes a little telescope and looks up at Jupiter for the first time. Now, I mean, the LIGO observatory was extremely sophisticated, but it's still just a beginning. It's really just a beginning. So, I mean, what else could we do? What else could we do? So LIGO I'm going to refer to it as something called a terrestrial interferometer. So it's a type of technology called interferometry. It is on the Earth, and it has gained the sort of first foothold in this gravitational wave spectrum. Okay, so I talked earlier about the full electromagnetic spectrum, how there are interesting things you could do with radio astronomy. There are interesting things you could do with ultraviolet astronomy. We have really just sort of tapped into one sort of gravitational wave band. And in the sort of grand scope of things, it turns out LIGO is basically an extremely high frequency detector. If you want to make an analogy to electromagnetic astronomy, it's kind of as though LIGO is like an X-ray telescope. It's like studying high frequency gravitational waves. Okay, now when you're talking about gravitational waves, what does high frequency mean? It means about 100 hertz. So these are, black holes that are orbiting each other, and near the end of their life, they're in spiraling. They're orbiting each other about 100 times a second. Okay, but that's the type of gravitational wave frequency that LIGO is sensitive to. And the types of sort of objects that LIGO could study were these things called compact binary systems. That is something like two black holes orbiting each other. Well, specifically two black holes that are on the order of 10 times the mass of our sun. One extremely exciting possible thing that LIGO could do, this is sort of the holy grail of LIGO's science case, is the study of supernovas. The Milky Way is frankly kind of overdue for a supernova. There ought to be a supernova going off in our own galaxy. I mean, any day. We're overdue because supernovae occur about once per century per galaxy. I think that's right. Maybe twice per century per galaxy. And we haven't had one that we know of for a very long time. If a supernova went off in our galaxy while LIGO was running, it would just be like stupendous. We would get so much information about what goes on inside an exploding star. Anyways, so beyond LIGO, what could we do? What else can be done? Well, you got to go to lower frequencies, okay? There's this project. The European Space Agency is taking the lead on it. They have a partnership with NASA. There are plans for the next decade to put this thing called LISA into space. LISA is similar to LIGO in that it is an interferometer like LIGO. LISA stands for Laser Interferometer Space Antenna. So this will be a very sophisticated, they call it a constellation of satellites that they plan on putting in orbit around the sun. It's going to be three effectively identical sort of optical devices that shoot very powerful lasers in this sort of equilateral triangle configuration. The sides of this equilateral triangle are going to be about 2.5 million kilometers. So I mentioned that just the way gravitational waves work, you kind of want to make your detector bigger to make it more sensitive. And so LIGO was 4 kilometers on a side. LISA is going to be 2.5 million kilometers on a side. LISA also has some other distinct advantages over LIGO. LIGO it loses sensitivity at low frequencies, specifically because it's on the Earth, and you start to run into seismic noise. Basically, the Earth is bumping around, and so if you want to like sort of overcome seismic noise, you got to get off the Earth, and that's one of the big motivations for LISA. And so it's going to have sensitivity. It's going to have exquisite sensitivity at sort of lower frequencies, at the so-called millihertz frequencies. So we're talking about things that waves that have wavelengths of like 10 light minutes, something like that. And the types of objects that LISA will be sensitive to, it's still these compact binary systems, things like 2 black holes orbiting each other, things like 2 white dwarfs orbiting each other, but it's going to be sensitive to many, many more of them. And you're also going to potentially start getting into this science regime of what we call binary supermassive black holes. So there's sort of this distinction between what we call supermassive black holes and what we call stellar mass black holes. So stellar mass black holes are black holes that get up to about 30 times the mass of our sun. Binary or supermassive black holes are things that are like 1 million times heavier than our sun. And we're pretty sure these things exist. We think that there's a supermassive black hole at the center of our own galaxy, but they're sort of unique beasts that we hope to learn more about in coming years from gravitational wave astronomy. Okay. So what else can you do? You have to keep going down to lower frequencies. You can use sort of conventional radio astronomy techniques. This is the Parkes Radio Telescope in Australia. You can use big radio telescopes like this to study arrays of pulsars over like decade-long time spans. And you can sort of do certain techniques and gain access to gravitational wave information still lower in frequency in what we call the nanohertz band of gravitational waves. And then you can study the cosmic microwave background to study these mind-meltingly low frequency gravitational waves. These types of gravitational waves that might sort of pop up in the cosmic microwave background are things that would have been generated like shortly after the Big Bang. These are like really exotic things, okay? Now, myself personally, I am a member of one of these pulsar timing arrays. This has been, since I was in graduate school, most of my work has been in this sort of area of pulsar timing. So I'm going to talk more about, how this might possibly work. So specifically, I'm a member of this group called NanoGrav. It stands for the North American Nanohertz Observatory for Gravitational Waves. We're an ever-growing collaboration of, I probably need to update this number. I don't know exactly how big we are. We're growing pretty quickly for reasons I'll talk about soon, but let's say on the order of 150 or 200 people. We're astronomers, data analysts, and just gravitational wave experts, a pretty diverse cohort of people actually with all kinds of expertise, various career stages. I've been a member of NanoGrav since I was a graduate student, and then as a postdoc, and now as a professor. The number of universities affiliated with NanoGrav is ever growing. Yeah, actually, so this is a photo of one of our meetings that was in Green Bank, West Virginia a few years ago. I'm actually all the way on the right in this photo. Yeah, anyways, so what does NanoGrav do? Well, it's something called a pulsar timing array. That's the title of this slide. What do pulsar timing arrays in general do? So yeah, we use truly world-class radio telescopes like the Green Bank telescope here to monitor the behavior of dozens. I think our number is upwards of 70 now of these things called millisecond pulsars. We've been doing it since 2004. And the goal, our sort of science case, is to find evidence of gravitational waves from supermassive black holes. So specifically, these supermassive black holes that are found at the centers of galaxies that have anywhere from millions to billions of times the mass of our own sun. Okay. So, I mean, what are these millisecond pulsars that we observe? So pulsars are the sort of dense remnants of exploding stars. Certain stars that are more massive than our sun, when they near the end of their life, they go through a specific type of supernova called a core collapse supernova, and they leave behind this sort of super dense nugget of extremely dense material. They have very strong magnetic fields that produce something that I think of as sort of like a radio laser. It's sort of not well understood how they work, just because these are the most like extreme environments in the universe. Unbelievably dense objects with unbelievably strong magnetic fields, and they're spinning very quickly. In fact, let's see, do I say that on this slide? Yeah, so Nanograv specifically studies this class of pulsar called a millisecond pulsar. These are pulsars that are spinning hundreds of times per second. And so you have an object, they have the mass of maybe twice the mass of our sun, but they're only about 10 or 12 kilometers in radius. So they're like the size of San Joaquin County, even though they're like twice the mass of our sun. But then you take something that big and you spin it, like, I think the fastest spinning one is like 700 times per second. And you also put like the strongest magnetic field in the universe on it. Sorry, that was my cat's automatic feeder going off. That if you heard that noise. Anyway, so these things are just extraordinarily exotic and extreme. Nonetheless, you have this thing that's spinning hundreds of times per second, and they spin incredibly regularly. And so what we do in Nanograv is we observe them as though they were just clocks. We do our best to just treat them as ticking clocks. And frankly, they're really good clocks. Many of them behave with timing sort of stability on par with really good atomic clocks here on Earth. And so, I mean, this is sort of like an ideal, this is something Einstein, I think, would have been in love with. It's like literally we have very good clocks in space, like spread out throughout our own galaxy. It's nearly a perfect thought experiment, okay? And so, we're observing all of these nearly perfect clocks in our own galaxy. We're trying to detect gravitational waves from the mergers of supermassive black holes. And so I've already mentioned this a little bit. I mean, so here's an image of two galaxies merging. We know that galaxies merge, okay? We also, just in the last couple of years, have very direct evidence of the presence of these supermassive black holes in the centers of essentially every galaxy. So this is a result from the Event Horizon Telescope that came out, I don't know, about 2 years ago now, where we've sort of directly imaged the supermassive black hole in a neighboring galaxy, in one of the most nearby galaxies. And so we're pretty certain that nearly every galaxy has one of these billion solar mass black holes in its center. We know that galaxies merge. We think that when two galaxies merge, eventually the two supermassive black holes at their centers will sort of come together, and you'll get this just incredibly energetic, massive thing orbiting around each other, producing these incredible gravitational waves that just happen to be at very low frequencies, the types of frequencies that we're hoping to study with pulsar timing arrays. And so a sort of, oh yeah, this is more or less what I just said. So this is a bit of a technical detail, but I think it's important for people to kind of imagine what we're trying to do with pulsar timing arrays. So we don't really understand the population of these supermassive black holes, but given our best guesses about what the population should look like, we think that we're more likely to detect sort of the choppy ocean of gravitational waves rather than sort of a coherent sort of the waves coming in one at a time. What I mean by that is we anticipate initially detecting a seemingly random superposition of many gravitational wave sources, kind of like this image on the left, rather than a single individual bright gravitational wave source like you might imagine in the image on the right. Okay, so we're just trying to find evidence of being on sort of a choppy sea of gravitational waves in this nanohertz band. So this is a sort of good cartoon of what this looks like. So we are here on Earth. We're using these big radio telescopes to study the behavior of these pulsars spread out throughout our own galaxy. And we think underneath, there's this sort of rippling ocean of nanohertz gravitational waves. And so we're just looking for these very specific patterns of timing abnormalities in the behavior of these otherwise nearly perfect clocks. Okay, so that's the sort of, that's how our experiment works. Okay, and we think we're getting really close. Actually, we think we're almost there. In December of 2020, we released an analysis of what's called our 12.5-year data set. So Nanograv started collecting data in around 2004. Over time, our data collection has gotten much more aggressive and sophisticated. And so our data set's getting better all the time. In this 12.5-year data set, we're starting to see evidence in our data that looks like what we think it should look like. Now, this is just the very nature of our experiment, is that it takes a long time. These are very low frequency waves that you don't sort of study overnight. You have to take data for decades. And so what you can see is what this graph on the bottom left is showing. Basically, at the low frequency end of this, we're starting to see some power in our data set that resembles the types of signatures we kind of expect to find from this so-called stochastic background of nanohertz gravitational waves. So this is not, we have not claimed like a detection of gravitational waves yet, but we think we're very close. This paper made a few waves. Sorry, that came out. I didn't mean that as a joke. If any of you are familiar with the popular web comic XKCD, we right after this paper came out, we got an XKCD comic about it. It's a terrible joke, but nonetheless, we sort of were internet famous for like a day. So this person is saying, ask me what the secret to detecting gravitational waves using pulsars is. What's the secret to detecting timing? So we do pulsar timing, and we think we're on the verge of detecting these gravitational waves. So it's a very exciting time to be in a pulsar timing array. We are currently working on our still yet more new and improved data set. We have, we're working on our 15-year data set now. And again, we think we're really close to making a sort of confident detection of these gravitational waves. And so, yeah, we think pulsar timing arrays are sort of the very next frontier of gravitational wave astronomy. We are confident that we're going to make, we're hopefully optimistic that we will make a confident detection in the next 1 to 4 years. We're at the cusp, we think. Okay. So once we make an initial discovery, it's just sort of opening a new can of worms. We've sort of opened a whole new window on this gravitational wave spectrum. We expect an initial discovery to be followed by decades of hopefully very productive scientific exploration. We're going to find individual supermassive black holes, black hole binaries. We could study alternative theories of gravity. Maybe we find evidence that Einstein's theory isn't working like it's supposed to. And just like any sort of new era of exploration, you kind of hope to find the unexpected. Who knows what we'll find? Let's see, what time is it? So there's sort of this sort of desert in the gravitational wave landscape that I'm a little interested in. I've done some thoughts, or I have some thoughts on how basically there's a big gap between what we study with pulsar timing arrays and what you might hope to study with the cosmic microwave background. It's uncertain how we could ever sort of probe this area of the gravitational wave spectrum. I think there's some hope for using things like, this is the Gaia spacecraft. So Gaia was an instrument from the European Space Agency that basically just measured the positions of like billions of stars with really high precision. And I think that instruments like this have a potential to sort of fill in this gap, because basically gravitational waves at this frequency, they'll sort of cause the stars to actually appear to wobble around by a very small amount in the sky, but like very small. And so you have to use something like Gaia, where you're measuring the positions of billions of stars very precisely. I think there is some potential there. And if you can get something like that working, you've covered the whole gravitational wave spectrum. So I think this is sort of the future. I'm kind of gonna, there are some interesting science problems that you could solve in this sort of desert. There's this thing called the final parsec problem, where basically, I talked about, we think that supermassive black holes come together and merge. There are just a lot of really open questions about exactly how you bring the two black holes when they're that massive together. And so that's kind of called the final parsec problem. Having some better sensitivity at these very low frequencies could help us answer that. It's an intriguing thing to try to do. And then finally, so actually, if I could be accused of being an expert on anything, it's this weird phenomenon called gravitational wave memory that I did a lot of my dissertation work on. It's sort of a unique thing that comes up in Einstein's theory of general relativity. I think there is some interesting areas to study this stuff called memory at the extremely, extremely low end of the gravitational wave space. And so I've been studying sort of possible signatures of this memory in the cosmic microwave background, which is sort of where you have to look if you want to do this extraordinarily low frequency stuff. And so, yeah, that's kind of what my most recent work has been on. I think that there's some interesting stuff to do there. Anyways, this is the sort of landscape of this entirely new field of gravitational wave astronomy. Again, I mean, we made the first detection of gravitational waves like 6 years ago. And so this is a new era. It's an exciting new era. We're learning about things that you can't otherwise learn about. And so I'm very excited to be a gravitational wave astronomer right now. So that's it. That's my talk. So thank you.
Took me a moment to unmute. Thank you, Dusty. That was wonderful. Are there any questions?
Yeah, Mike's got one here.
I'll go ahead and you can go first.
Oh. Yeah, Mike, you got a question.
Oh, okay. Dusty, I have a question for you. You mentioned there are different frequencies with gravity waves, and along with, say, the electromagnetic waves, where the frequency does affect the way it interacts with matter. Do gravity waves have the same thing, or is there any evidence that it might?
Yeah, so I think in theory, yes, but in practice, no. And it's because it takes, just to produce like the weakest gravitational waves, you need crazy things like merging supermassive black holes. Like it takes a lot to even produce gravitational waves. And then once they're produced, they don't actually sort of couple to matter very strongly. They produce these very, very small effects. It has to do with the fact that the force of gravity is just very strong compared to electromagnetic forces. So electromagnetic waves, they couple to charged matter like very strongly because actually the electromagnetic force is extraordinarily stronger than the gravitational force. But these gravitational waves, just the gravitational interaction is so weak that no, they don't interact with mass very much. So, I mean, one of the ways LIGO was able to confidently make a detection of gravitational waves was because they have these two different detectors, one in Washington State and one in Louisiana. With electromagnetic waves, just because you see something, if you saw something like coming from a star in Louisiana, you wouldn't necessarily see it at an observatory in Louisiana, or pardon me, in Washington. But these gravitational waves just move right through the Earth. And so, they were able to detect it in one of their observatories, and then like a couple milliseconds later, they detected the same thing in a few states over. And it's because these gravitational waves, they just pass essentially unimpeded through the Earth.
I've got a question. There's actually three, isn't there, three gravitational wave observatories? There's also one in Italy.
Yeah, so
And then,
it's actually called the LIGO-Virgo collaboration.
Right, right.
Virgo is the European effort. Yeah.
Right. So basically with those three, isn't that what's giving us some ability to detect the direction that it came from?
Yeah.
Okay. So with Lisa, you showed, basically you've got three of them, but it's still on one plane, so to speak. Won't we need several Lisas to give us that same ability?
I mean, that's a very good observation.
Or will that being so far apart, it would still be able to give us the...
So Lisa is going to be able to sort of tell you the direction to various gravitational wave sources. But the reason for that is because most of the sort of gravitational wave sources that Lisa will detect are sort of going to be persistent sources. They're going to be sort of like white dwarf binaries that are just sort of stably orbiting each other for like long periods of time. Whereas LIGO is detecting these sort of catastrophic bursts that are like very short episodes.
Right.
And so Lisa is going to have the advantage of basically being able to like observe these things like while it orbits the sun.
Okay.
And so you're going to be able to move the sort of detector around the sun and sort of see how the response of the detector changes as you still observe the same sources. So with that capability, you're going to be able to localize these things. The real problem that Lisa is going to have is actually that it's going to be so flooded with signal. It's going to detect every sort of compact binary in the Milky Way. And so it's going to have like tens of thousands of signals going off all at once. And so being able to sort of disentangle that thicket of signal is really the big challenge for Lisa.
Yeah, you're going to need a supercomputer to sit there and go through all that stuff constantly.
Yeah.
Okay. All right. Thanks.
Dustin, can I ask a question?
Please go for it.
Is there anything in the ether of space that has an index of refraction that we could maybe like focus these waves?
Yeah. So, I mean, so like there's these phenomenon called gravitational lenses. You can see sometimes if there's like a galaxy cluster that is very massive, you can see it sort of distorting the light from still more distant galaxies. And so like the light from very distant galaxies gets sort of lensed around foreground massive like galaxy clusters. Gravitational waves are subject to that same type of lensing. And so I think, so LIGO now has detected like a whole like dozens of events, gravitational wave events. There has been speculation that a few of these events were sort of further away than you would otherwise expect them to be, because they had been sort of magnified and lensed by like a foreground gravitational lens.
That is cool.
Yeah.
Dusty, I have a question. Excellent presentation. Thank you very much.
Yeah, thank you.
You started off saying that gravitational waves are founded in Einstein relativity.
Yeah.
So my question is, do the gravitational waves also align with any of the quantum physics theories? Or is that not really a valid question, since there's not really particles or matter in gravitation waves?
Yeah, so I mean, that is a good question that is like, I will say like a little bit of beyond my pay grade. I can kind of give you an answer to that. People do talk about gravitational waves in sort of quantum mechanical ways. So for instance, you have in quantum mechanics, you have like fermions and bosons. So like electrons are fermions. They have spin half. They're spin half particles. In a quantum mechanical sense, photons, so just standard electromagnetic waves, they are bosons and they have spin 1. They're spin 1 particles. If you kind of keep doing this sort of treatment of fields and radiation in these fields, you can do a similar treatment to gravitational waves. They are a boson, like light, but they have spin 2. They're a spin 2 field, and so they behave a little bit like light. But yeah, I mean, I will say that's a bit beyond my pay grade. I kind of gave you the understanding of it.
Where I was going with that question was to see if there was any possibility that the new gravitational wave discovery will go to support that unified theory that's so elusive.
Yeah, I mean, so that's actually something that people in LISA are interested in studying. So one of the very exciting types of objects that LISA could study is something called an extreme mass ratio in spiral, where you have something like a supermassive black hole. So something like one of the supermassive black holes at the center of galaxies, so 1 billion solar masses, say, and you have a more normal sized black hole, something that's just like 10 times the mass of our sun, orbiting it. And there are certain ways in which that could potentially behave a bit like a gravitational atom. You basically have like a little black hole orbiting a nucleus sort of thing. And so there could be some like, who knows what that would look like, but there might be some weird like quantum gravity phenomenon going on there.
Oh, this is great. It'd be so exciting to see this new field of study emerge right before us.
Yeah.
Well, I'll pop a question in here, Dusty.
Yeah, go for it.
Yeah, I'm a little confused as to what you're looking for in pulsars. So you time the periods of all these pulsars. Are you looking for variations of their timing that would indicate a gravitational wave had passed through?
Yeah, so that's a great question. So pulsars, millisecond pulsars in particular, are very good clocks, but they are not perfect clocks. So we compare them against like a sort of terrestrial time standard. So like, I mean, the National Institute for Standards and Technology like spends a lot of time like trying to keep like a very regular clock. And so we compare the sort of behavior of these space-based clocks to our local time standard, and they do wander a little bit. Their sort of timing is not perfect, right? And in part that's because they are unique butterflies, each and every one of them. They are astronomical objects. They have their little quirks and stuff, right? And so you know they don't behave like perfect clocks, but because we observe like over 70 of them, what we're looking for is sort of correlations in their timing irregularities. There's no reason that like two pulsars that are on like opposite sides of the sky and are thousands of light years apart should be behaving in anything resembling the same way. If they do have correlated timing irregularities, it's because we here on Earth are sort of bobbing up and down on this sea of gravitational waves. And so we're looking for specific patterns of timing irregularities between our sort of array of pulsars. Specifically, we're looking for something called Hellings and Downs correlations. That's the sort of technical buzzword. These Hellings and Downs correlations are like a very specific prediction of general relativity.
Very good, thank you. So yeah, that clarifies one thing. I was thinking of, you were looking at like a gravitational wave that was affecting the two or more of your array, but it's actually the wave affecting us where we're making the measurement from.
That's right. We're basically trying to like see evidence of the Earth sort of bobbing up and down. Yeah.
Very nice.
I have another question. If you've got orbiting pulsars over here, and they've got a timed wave putting out, and got another one here, another one over here, won't there be places in space where it's like a constructive interference, like a hot spot between them?
But for the pulsars?
For the waves from the pulsars.
Oh yeah, I mean, so there's definitely constructive interference. I mean, these waves, they superpose on each other just like any other wave. And that's what we are trying to detect, actually. I mean, we're trying to find, there's basically so many sources that are contributing to our signal that we just call it like a stochastic background, because I mean, it's just like waves in the ocean, right? So when the ocean is very choppy, you could decompose that into just a bunch of like coherent waves. But when you add enough of them together and they're sort of randomized, it is just all like constructive and destructive interference. But if you have enough of it going on, it just kind of gets kind of chaotic and randomized. So there's a lot of constructive and destructive interference going on.
But couldn't there be an organized hotspot node between regular periodic waves? Do you know what I mean?
Yeah.
Like a standing wave.
Yeah, exactly.
You know, I'd have to think about that. I think you would, I think it's possible, but you'd have to be lucky. Like we'd have to be in like a pretty special realization of the universe, I think.
All right, any more questions? And let's give our speaker another hand. Thank you very much, Dusty.
Yeah, thank you for having me.
Appreciate
It was a
that a lot.
pleasure. Yeah, it was a pleasure.
All right. And turn things back over to you, Mike.
All right. Well, again, thank you, Dusty. That was really interesting. I wish I could live long enough to see where this all goes. It sounds, for young physics students, wow, what a future. Makes physics really interesting. Okay, well, with that in mind, I want to bring up on May 7th, we've got our potluck over there at Oak Park. And it starts at 3. I think most of you know about that. It'd be nice if you could come. You can also get there earlier, and there will be things over there at the Science Center. I'm going to let Doug talk about that in a few minutes. As far as what to bring in the past, we've done different methods, but I think if everybody just brings whatever they want, please don't just all bring bread or peas or something like that. We can do a little better than that, but something that you would want to eat, so that all of us can share rather than just each of us eating our own food. It would be nice on that. Also, along with that, we've kind of come up with the idea that we do not have a guest speaker for that month, for May, for a general meeting. So we're going to go to the general meeting, and this will allow all of us, if we want to socialize, to get together at the actual potluck and catch up on things, since we really rarely, I think just one other time, we were able to do that at Jeff's school over there in Lathrop. So this would be kind of nice for all of us, just to see each other and enjoy each other's company. And then for June, everything will resort back to the way it was on that. Any questions or anything? And if not, I'm going to let Doug give his little talk about May 7th, especially earlier, before 3 o'clock. So Doug, go ahead. Let's hear what you have to say, please.
All right, so once again, like Mike said, it's our annual potluck. So we need everybody to come on out and to the park. But we're also trying to do something. It's also Astronomy Day. It's one of the reasons we do our potluck there. And if we had a Striking Sparks telescope application, then we'd be doing that also, but we don't have one. So because it's kind of we're trying to do is kind of a special day out there, it's going to get advertised a bit more. And we get the Poplar Pavilion comped to us for free by Sandy Adams, who is basically the marketing person for San Joaquin County Parks. And the reason she does this for us is because we bring people out to the park, and she wants to put on a bigger show at least once a year. And so this is our big show. So we were also going to have the Nature Center open, and we want to have activities for kids. So we'll have tables with various stuff for kids to do out at the Nature Center. So we need volunteers. We need people to help. So I know we've got some teachers in our group. We've got, family members and so forth that you might be able to twist their arms. I need people to sign up, call me and say, yes, I can help out at the Nature Center for an hour or so to work at a table and to help with either coloring or create a constellation or answer questions. That one might be a little tougher. I'm also, because I could not get a speaker from NASA, NASA never did get back to me on that with my request for a speaker. So I'm going to step up and I'm going to do basically a 1 hour what you can see in the night sky at the Nature Center, that room. But if we can get somebody else to do a 15-minute, a 20-minute, a half hour, an hour talk for the general public, that would be great. That way we can advertise that also. So it's going to be advertised in the newspaper. Sandy's talking about hitting radio stations and so forth with a public service announcement. So like I said, we really do need to show up, and we really, really need volunteers to come out and help at the Nature Center. And then as the day goes on, we'll close down the Nature Center about 6. And then we will go over and do astronomy in the park until whenever, people leave. So it's going to be a big meeting. We also need volunteers for Earth Day. Earth Day is April 24th. So we've been invited out to Victory Park. So we're going to need the solar telescope. We'll need a telescope, a regular planetary scope out there with a broadband filter, like we did for the STEAM event at Lincoln. So we need a couple of people. If they can do, a couple of people will show up in the morning. I guess I'll be one of them. I'm hoping Eric can make it on the 24th also. And then maybe we can get a couple people to come out at about noon and take over and till the end of the day, about 3 o'clock or so. So once again, I need people to email me, call me, whatever, and say, yeah, I can help out with that. Actually, Tim, if you can bring, if you're available, if you can bring that your new solar observatory thing with you, that would be.
Yep, I plan to be out there. Hopefully there'll be some sunspots to observe by then.
Yeah, and then, like I said, if we can get somebody out there that can maybe grab Jupiter or Venus during the day, that would also be a help. So this is our chance to get back and start doing some public astronomy and make an impact out there, so that kids like CJ there can meet us and talk to us. Hey CJ, if part of this talk was a little over your head, don't worry about it. It was over most of our heads also, okay? You're in good company. And if you got questions, just ask. So anyway, like I said, I need everybody to email me and tell me that, yeah, I can help out on Astronomy Day and at a table for an hour or so. And same thing with the Earth Day, if they can do that for me. That's about it, I think.
Okay.
Back to you, Mike.
Doug, I just want to clear one thing up. On your announcements, you have potluck in the park at 1 p.m.
Oh, okay.
Yeah, I made this slide.
Yeah, actually, I plan on being out there about noon to start getting stuff set up. And set up the, we can set up the solar.
Pretty much when are the eats going to start? When is everyone going to sit down?
I thought normally we did that about 3, but
Yeah,
Gary, isn't that about when we usually did it?
Food?
Food, Jerry, food.
Oh, I kind of thought that was a little later in the afternoon, but
Okay,
no, we're flexible.
yeah.
Right.
So,
Sounds
I mean, if you can get out there, I'm not asking everybody to show up at 1, but if they should, everybody should be there somewhere close to 3. And if you're going to help out with the activities and so forth, yeah, please come. We need a few volunteers to get there by 3 o'clock to help with the activities. So.
all right, very good. I was going to say a pun, I'm not going to do it, so we'll just
Oh,
continue
come
on.
on.
Well, you mentioned that astronomy is very challenging for young people, but I think astronomy is over everybody's head. Pun intended.
Ah, very good, very good. Yeah. Of course, not gravitational waves. That comes from underneath too. Ooh, bad.
All right. Okay. I think Jeff's going to do the fun part here. This is where we give away a Starbucks card.
Oh,
Hey, Mike, before we do that,
Sure.
hey, Jeff, you brought to our attention that May 15th, there's a total lunar eclipse. Do you want to talk a little bit about what that's going to be like?
Sure. So on everybody's calendar, like if you have a calendar and it says the full moon's on the 16th, it's a universal. Night.
Thank you.
It's a universal time date. Pacific time, it is the evening of the 15th, which is a Sunday. And the moon will already be in partial phase well into it when it rises. And only a few minutes after it rises will it begin totality. So when the moon rises, it'll have a little bit of sliver left to it, and within a half an hour, maybe within 25 minutes, it will be fully engaged into totality. So it'll be a toughie at first. And so by the time the totality is going to last 85 minutes, so by the time totality ends, it's still only going to be about 15 or 16 degrees high. So the good news is it's a primetime eclipse instead of one of those pre-dawn nasty things. The bad news is being so low in the sky, it's going to be challenging just because it's going to be a while before the sky gets dark. And that's when the moon's going to be in eclipse. So good news and bad news kind of eclipse. So I'm going to go to Highway 4 to observe it because low in the southeast is pretty good at Highway 4, but even then it's going to be difficult to see until it gets a little bit darker after the sun gets further down under the horizon. I would say it'd be neat to have someplace in town where public can observe it, but because of this not full dark problem we're going to have, this may be a very difficult eclipse for the public to see, and it'll be in the buildings and trees because it's on the horizon.
yeah.
So it's going to be perfect for prime time. You don't have to be up late to watch it. And it's a very long eclipse, 85 minutes. But by the time the sky is dark enough to enjoy it, the eclipse will be working its way out. So I don't want to say don't go observe it, but I'm going to go observe it. But it may be more difficult than we think. So that's Sunday night, the 15th of May.
Okay.
Hey, Jeff, you also sent me a photograph a week or so ago of a photo that you took. And we're all interested in where you took this photo from.
Yeah, I had to go to Uranus to take this photograph. I saw this on, I'm on a group on Facebook called Bad Nuclear Jokes, and it's a bunch of nuclear engineers that have very sick humor. And one of them posted this the other day, and it's a transit of the planet Saturn, which is impossible from the Earth, but I still thought the guy did a good job of it.
Very good.
While I've kind of got the floor here, I'll go ahead and go on to our Starbucks card thing here. Our winner for the Starbucks card is Ed Reibel. Congratulations, you got the Starbucks card. And Mike Beisel, so thank you, Mike.
Yeah, you're welcome.
Thank you, Mike.
Now, here's the thing. Ed, are you still out there?
Yeah,
He's
man.
still here.
I'm here.
Okay, good. Hi, Ed.
Hey,
Congratulations.
hey.
Okay, all right, folks, now that we're done with that, any other business that needs to be brought up or discussed or any questions? You had a good night. Everything worked out pretty well. We had great speakers. Thank you, Jerry. That was outstanding.
Yeah, very good.
Well,
Thank you,
Very
Dustin.
clear,
Thank you.
very
You're
easy to
welcome.
understand, certainly knows the subject. And I hope we can have him back again. So
well, we
maybe,
know where he lives.
you can schmooze a little bit. Maybe you can get him to come back and talk to us.
Oh, certainly.
Okay.
Hey, Jeff,
Okay,
you
folks.
got your garage floor finished and you're inviting us over for ATM on Saturday, huh?
Not Saturday this weekend, but Saturday next weekend. My garage is a complete disaster area. I've moved everything out of my classroom in there. I've redone the floor. I've got equipment in there, and it'll be a miracle if I can get it ready for a week from Saturday. But yes, Saturday, what is that, the 23rd?
I don't know.
Okay,
Yeah.
what is it? Yeah, I think, okay. Yeah, we do have an ATM. I'll make it happen. It is a mess. And so it'll be fun. I've got so many projects I'm just not finishing right now. It's ridiculous.
You will, now that you're retiring.
Yeah.
So it's going to be fun. So that's pretty exciting for Jeff. I think we ought to do something for Jeff when he retires. Maybe kick him out of the club or something useful.
Thank you. Thank you very much. Thank you.
I was thinking the other way, make him do more.
Yeah.
He have more time on his hands.
Block on that one. Oh, well, anyway.
Send a sympathy
Okay,
card to Glenda.
Yeah, she's going to get sick of me in about 10 minutes.
Yeah, I sort of went through that too. So after retiring.
You got sick of Jeff?
What?
No, that too, of course. But
Oh, yeah. Thanks, guys.
anyway, okay, folks, anything else? Okay, if not, I need someone to adjourn the call for adjournment of the meeting there. Is there a motion to adjourn?
What were you looking at me for?
Yeah, just say yes.
I'll make
Yeah,
a
I move we
motion to
close the meeting.
adjourn.
All right, anyone else?
I'll
Need
second.
a second.
I'll second.
Okay, meeting adjourned. God bless you all. Take care.